Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your Zybooks section 9.5, number representation. So it's been brought to my attention that the first video I made cut out in the middle of it, and I guess I must have accidentally hit the stop button, which is right next to the pause button, and then I continued recording, oblivious to the fact that I wasn't really recording, and I apologize for this. So this is part 2. This is just going to start where I left off in that last video on number representation, which was here. It was in this activity where you were asked to find, you were given a number in decimal and asked to find its base, whatever expansion, right? Represent it in a different base other than 10. And I showed you at the end of the last video before it cut off, I completed this example, writing the number 67 in base 6, and it really just I did a bunch of division by 6 and then looked at the remainders, and those remainders are what made up the digits of the expansion 151. So I'm going to do the same thing here with 27, find the binary expansion of 27. Alright, so I'm given 27 in decimal. Maybe I'll write it down here because I want to do I like writing the long division stuff. And then we're doing base 2. Right, we're changing it to its base 2 representation. So I'm going to first divide it by 2. And you find the quotient. How many times does 2 go into 27? That'd be 13. With what remainder? And that would be a remainder of 1. Okay, and if you recall from the end of the last video, again before it cut off in part 1, this remainder of 1 here is going to be the rightmost digit in my binary representation of the number 27. Right, and then I just keep, I like doing this way, where I keep going up, and you keep going until you get a quotient of 0. So then what's 13 divided by 2? I just keep dividing by 2. 2 goes into 13, 6 times. Also with a remainder of 1. So 1 will be the next digit in the binary expansion, the binary representation. Then I divide 6 by 2. Quotient's 3 with a remainder of 0. Right, because 2 goes into 6 evenly. Then divide 3 by 2. 2 goes into 3 once with a remainder of 1. Then finally divide 1 by 2. 2 goes into 1 0 times, right? And this is where you stop, when you get a quotient of 0 with a remainder of 1, right? Because 0 times 2 plus 1 would be 1. And then reading it from top to bottom here, I get 27 in decimal is the same number as 11011 in base 2 in binary. Okay. And you can check this, take take 2 to the 4th plus 1 times 2 to the 3rd plus no 2 to the 2nds plus 2 to the 1st plus, and then 1 2 to the 0 plus 1. This is 16 plus 8 plus 2 plus 1, and you're going to see that that is indeed 27. So this is correct. Okay, so again, I feel easy to take a number in decimal and express it in terms of some other base, right? Just keep dividing by that number, by that base number. Okay, and they put it all in terms of divs and mods, right? That's what I was doing, right? Your divs are your quotients, and your mods are your remainders. So they ask you to do the same thing here. Take 57, just keep dividing it by 5, and looking at the remainders. And then again, you just stop when the quotient is 0. Here, 52, just keep dividing by 7 to write it in base 7. And 21, just keep dividing by 2 to get binary, right? Write it in base 2. All right, and you're asked to do the same thing in the challenge activities, it looks like. Here's 28, written in base 2. Let's see what this last level looks like. Yeah, a little bigger number, but not that huge. 1,295 in decimal. Can you express it in base 8 digits? Pardon me. Alright, and then the final part of this section is on the number of digits required to represent a number. Alright. So it says here there are many algorithms that operate on integers whose running time depends on the number of digits in a decimal expansion of the input value, or the number of bits in a binary expression. Therefore, it is useful to know, in general, how many digits are required to represent a certain integer, a positive integer n, in its base b expansion. So remember, if you're in base b, the digits that you use range from 0 to b minus 1, right? Remember, when you're in decimal, base 10, the digits are 0 through 9. When you're in binary, right, base 2, the digits are 0 through 1. Now I know when your base is bigger than 10, they start using letters, but those letters represent numbers up to b minus 1. Remember, hexadecimal, base 16, you got digits 0 through f, where f represents like 15. Which is 1 less than 16. Okay. So, the largest number that can be represented with k digits in a base b expansion is the number whose digits are all b minus 1. Alright, for example, if I said, what's the largest number in decimal with 5 digits? Well, the largest number in decimal with 5 digits is when they're all 9s, right? 99,999. So that's what they're saying here. The largest number that can be represented with k digits in a base b expansion is the number whose digits are all b minus 1s. Alright, the next highest number, right, when you add 1 to that, is the number represented by 1 following by k zeros. So again, their example here, if the base is 5, the highest value digit is 4, right? When you're talking base 5, the digits are 0 through 4. So the largest number that can be represented with 3 digits, base 5, is 444, which is 1 less than 1000. And again, this works out the same for, I'm just going to pull paper up on the screen here. This works out the same for decimal. Alright, this works out the same for decimal. If we're in base 10, right, if we're in decimal, and I say, again, like I said earlier, what's the largest decimal number with 5 digits? That'd be 99,999. Which again, if you just add 1 to this, right, this is 1 less than 1 with 5 zeros after it. Right, it's 1 less than 100,000. But this, this number of zeros is 5, the same as the number of digits in the 9999. That was just 1 below. Okay. So the value of 1000 base 5 is 5 cubed, right? Just like, I don't know why I put this away. Just like the value of 100,000, if you're talking decimal, is 10 to the 5th power. Right? 10 to, and then the number of zeros is the power on the base 10. Just like here, right? Just like here, the number of zeros at 1 followed by 3 zeros, base 5 is 5 to the 3rd. Okay, so it's very similar in any base. Alright, so the figure below illustrates this idea with arbitrary values, right? So again, if you're looking at what's the largest number represented by k digits, base b, that would be the number with all k of them being the digit b minus 1. Right, like all 9s or all 4s in base 5. And this is just one less than 1 with k zeros after it, base b minus 1. This is actually equal to 1 with k zeros after it minus 1. Right, because if you take the 1 with k zeros after it, that's b to the k. Right, the representation of b to the k power. And then subtract 1 and you get that largest number with all k digits. Right? Therefore, if n can be represented with k digits base b, then n must be less than or equal to this guy here, less than or equal to b to the k minus 1. The number of digits required to represent the base b expansion of n is the smallest integer k, such that n plus 1 is less than or equal to b to the k. So all they did was add 1 to both sides of this inequality here. And if you look at the logarithm of both sides, you'd have the log base x equals the log base b of n plus 1 is the real number, such that n plus 1 is equal to b to the x. So certainly the number of digits must be an integer, and the number of digits must be at least this log base b of n plus 1. Therefore, the number of digits required to express the base b expansion of a positive integer is this. It's the ceiling, and hopefully you remember the ceiling function, of the log base b of n plus 1. Alright, for example, the number of digits required to express the base 2 expansion of 13 is the ceiling of the log base 2, right, base 2 of 13 plus 1, right, the number you're talking about, plus 1. So that ceiling would be 4. And let's see if that's true. Does it take 4 digits base 2 to express the number 13? Again, I'll just do it on the paper on the screen here. Now 13, the largest power of, I mean, you could do the division by 2 thing that I did earlier, but I'm going to write out the powers. This is 1 times, 2 to the 3rd. It's basically 8 plus 4 plus 1, plus 1 times 2 squared, plus 0 times 2 to the 1st, plus 1 times 2 to the 0. So 13 is 1, 1, 0, 1, base 2, and there's your 4 digits that they were talking about. All right, they said it takes 4 digits in binary to represent the number 13. And that's what this is all doing here. Right? That's what this is talking about. So that, again, this ceiling of the log base b of n plus 1 will give you the number of digits in that base it takes to represent the number n. Alright, where n is in decimal. Alright, so question, how many digits then would be required to express the base 7 expansion of 2401? Well, it'd be the log base 7 of 2402, right, remember n plus 1, and then the ceiling. Alright, let's see what that is. Now, I'll pull up paper here. Now if we look at the powers of 7, right, 7 to the 0 is 1, 7 to the first is 7, 7 squared is 49, 7 cubed, 280 plus 63, 343, 7 to the fourth is 2110 plus 280, 2380, 2401. Right. So and the 7 to the fifth would be a lot bigger. It'd be 14,000 something. No, it'd be more like 16,000 something. But still, so the log base 7, and I guess I could use a calculator for this, but the log base 7 of 2,402 would be something between 4 and 5, right? Because 7 to the fourth power is 2,401. So this is this is 4 point something. I don't know what. So then the ceiling of this, right? The ceiling of this log base 7 of 2402 is 5, right? So that means if I were to write 2,401 base 7, it would take 5 digits to do that. Now let's see, 2,401, well remember I already said it was 7 to the fourth. And 7 to the fourth, when you're writing base 7, would be 1 with 4 zeros after it. Right? It's 1 7 to the fourth, 0 7 cubed, 0 7 squared, 0 7 to the first, 0 7 to the 0. All right. So see, it takes 5 digits base 7 to express the number 2,401. And again, that's all this formula is giving us, this ceiling of the log base b of n plus 1. Alright, so the rest of these are pretty simple, I feel. How many digits are required to express the base 8 expansion of 9? That'd be the log base 8 of 10, and then the ceiling, which would be 2. Right? It would take 2 digits to represent 9 base 8, and just 1 1. How many digits are required to express the binary? Now remember, 2 to the 55th, if you're doing binary, 2 to the 55th would be in binary 1 with 55 zeros after it. And 1 with 55 zeros, that's 56 digits. And then same thing here, how many digits are required to express the base 8 expansion of 8 to the 7th? See, base 8, the base is 8 here. So 8 to the 7th, if I expressed it in base 8, would be 1 with 7 zeros after it. And 1 with 7 zeros after it is 8 digits. Oh no, I'm sorry, I missed the minus 1. I was looking at just 8 to the 7th. I apologize. It says how many digits are required to express the base 8 expansion of 8 to the 7th minus 1. Remember that 8 to the 7th minus 1 would be the largest number with 7 digits ever, right? See 7 sevens. Okay, I'm sorry, I didn't see the minus 1. I was jumping the gun there. But if it was just 8 to the 7th, it would be 1 with 7 zeros. Right, but then the minus 1 takes it to be the largest number, base 8, with 7 digits, and that would be the 7 sevens, like you see in the answer explanation here. Okay, so again, sorry about the fact that part 1 got cut off. Hopefully the rest of this made some sense. And you have your additional exercises, which again, some of these are assigned, some are not. I'd still recommend looking at all of them, just to try to get more practice, get more exposure to the material. You also have the solutions you can look at, but please try to work them out before you look at the solutions. Right? You're not going to learn anything if you're just copying solutions down. And if you have any questions or notice any other glaring errors that like another thing about my videos cutting off, but it's not here. I'm seeing that I'm actually recording. I'm actually paying attention this time. send them my way. Send me a message and I'll get back to you as soon as I can. And thank you very much for watching.